Have you ever seen AI behave badly? Here, I'm asking it to research what makes the hardest bars, a question many people have wondered. Here's the problem though. Is there a right answer to that? I don't think so. I think you know a bar when you hear one. We'll start with some mid-AI generated bars and get to the good stuff later.
Train deep, deploy white, stroke, slow, stroke. Train deep, deploy white. Stroke, slow, stroke. Train deep, deploy white. Train deploy. Give them Blackwell super chip, I ate the whole grid. Unified memory flood, watch what the written did. To the core smoking, yeah, the red light beaming. Collecting Skywalker data, hologramming. Jupiter's driven, dripping. Stepping like a loud pipe, stop, gripping. Symbol pipe, Skywalker, the baby never stopping when dreaming.
Let's start with this idea. Scale is all you need. This has been prevalent in the space because compute is cheap compared to being a clever little boy who knows everything, which is expensive. That's absolutely true. Should you require all of your developers to go get math, stats, and linguistics degrees so that they're able to build the best system possible? Or is it okay to build a system that works where you don't need any additional skills or education? You only need 500 gigs of VRAM running for like a week. It's a fair question. I have my opinion on it, but I don't think there's a one-size-fits-all answer to that question. So here's another question to think about. What if, instead of needing to go and get all of that academic expertise and validation, paying hundreds of thousands of dollars in tuition and living expenses, not to mention decades of your life, what if you could develop it yourself? You save money, you save time, and you develop real expertise. Especially in the climate where more and more teams are discussing going on-prem with their compute. This can feel a bit like going up against something crazy, something cosmic and eldritch, if you look at it as a zero-sum game against Google and the Gemini models, but the reality isn't scary at all, because you're not competing with them. See, Google and the other LLM providers are chasing AGI, which with LLMs, in my opinion, is a dead end. And that's been said by researchers, again, myself included, for years now. I don't need my coding assistant to be able to also give therapy to Victorian-era peasants or to be good at it. I need it to be a good coding assistant. But Google does need the first use case because they're chasing AGI. They need to be able to appease all people in all cases. So, I got my hands on $17,000 of hardware. So you don't have to. You can learn from my mistakes. If you've made it this far in the video, you're one of 3 people. You already have a home lab and are hoping to find out about my experience and recommendations. You are in the process of starting a home lab and are looking for the same things. You maybe are even comparing these devices. You do not have a home lab and you aren't planning on building one. This is just an interesting subject to you. Whichever you are, thank you for being here. This video has been a long time in the making. I've previously made videos and written books like LLMs in Production that contain information about successfully self-hosting AI models on arbitrary consumer hardware, from Raspberry Pis to RTX series gaming computers. So, let's look at the hardware we'll be testing and what I'll be showcasing for you today. So, the Framework Desktop is one of a number of PCs that have been released recently with the AMD Ryzen AI Max Plus 395 128GB unified memory setup. I don't consider Framework to be necessarily better or worse for this than any other provider, and some others I'd recommend are B-Link and HP. But I picked the Framework because they advertise increased customizability. Unfortunately, I haven't found a provider of this type of machine that doesn't solder the RAM and processor in, so that customizability is limited regardless of who you choose. The system cost me about $2,500, and I ran into some trouble setting it up that I'd like to share with you to give you a full picture of what you get when you're picking one of these systems. So first, they're not readily supported hardware at the OS level. It's likely they will be in the future, they're just new, especially given how many brands are actively pushing this chip. Like, you can get it from Asus, you can get it from anywhere, but there's an interesting lack of support when it comes to AMD themselves. Lemonade Server, the best and easiest way to use AMD chips for LLMs because it's developed by AMD engineers, only supports the AIMX Plus 395 on machines running Windows. When I began to set up the desktop after it came, I started with Bazzite as my first instinct. As far as all regular usage of this type of setup, I'd go so far as to say this is the best OS for it. It comes with support for the hardware and firmware to make it easy to apply the hardware power to gaming and office functions, but it was very difficult to extend that support anywhere in the ML direction, so my next idea was Ubuntu, only because of how ubiquitous it is. I've had good experiences with Ubuntu and other hardware setups, namely Nvidia-based ML server setups, because I'm not a stranger to installing and using different versions of CUDA, CUDA Toolkit, and NVCC. On the framework though, that was not a good idea. I spent weeks and weeks with framework customer service trying to make it work, but Ubuntu OS really doesn't play nicely with the framework desktop hardware, specifically the Wi-Fi card. It's a MediaTek card. If you know what that means, you know. This was after checking kernel logs and Linux error logs and running Memtest 86 Plus and passing, only for freezing and glitchy visuals to continue. For anyone else exploring this path, I settled on Fedora 43 and discovered the Qzo GitHub repo with the toolboxes available specifically for this purpose on this OS. It is not an ideal setup to be working out of a toolbox rather than on bare metal for me and for actual model performance, efficiency, and throughput, but it is comparatively very easy to work with. On this note, there's one supported kernel version, and newer kernels break RockM, so that's where the server will have to live for now. I sincerely hope that AMD will divest from whatever their Microsoft partnership looks like now. I don't even know if they're partners, it could just be a Microsoft lobby, and begin supporting their own hardware soon. Because this is a fantastic device for the couple of things that it is really good at. By contrast, the DGX Spark was an almost painless setup. I set it up over the network, and Nvidia isn't shy at all about leaning into the desktop server marketing that they have going for this device. They really want you to connect with Nvidia Sync, but when I went to try it out, there were nothing but connection issues. On the plus side, SSH tunneling with ports for the Spark dashboard and any other services you'd want work perfectly. The Spark runs a modified and currently supported version of Ubuntu, and it comes pre-installed with the Nvidia stack. The main issue that I've found with this is that all of the ML frameworks and libraries that you would want to use end up being unsupported on bare metal. And to be frank, I don't see Meta or Hugging Face or even TinyGrad for that matter tripping over themselves to support the Spark's hardware in their ecosystems anytime soon. You can do it, and I managed to get PyTorch and Unsloth both, also TinyGrad, using the GPU outside of the Docker container Nvidia recommends for development, but honestly the gains are not worth the effort. This device is clearly built with data scientists in mind, with a button to open Jupyter Lab prominently displayed on the DGX dashboard. That's actually where I got the idea for this video. It's a simultaneous comparison of these devices, along with a bit of tutorial trying to hit from both sides. For the data scientists, this will hopefully help you upgrade to be able to pass models and data off confidently to other teams without worrying about dependencies or their ability to run, test, and deploy what you built. And for the ops and developers on the other end, it's a bit of a tutorial on what the data scientists should be doing to make your lives easier. Mac Studio. So, Core ML is an absolute mess. Apple has given up on ML. They are completely outsourcing their ML development to Google. That was announced on the 13th of January. Don't do anything with a Mac Studio except run LM Studio or MLX. So, for the data scientists, I want to ask a question. You've got your data, you hit your metrics, you trained your model, now what? And for everyone else, Why is it so damn hard for the data scientists to throw something coherent over the wall instead of a Jupyter notebook or a mess of Python files and dependencies? The answer to both of these questions is unfortunately so many reasons, which is why we have multiple companies popping up specifically to solve these problems. And we're lucky that so many of these companies are open source or at least source available so that we can test things out in safe environments and we can make mistakes where it doesn't matter. In the graduate course that I teach at Utah State University, we use ZenML specifically for this. We want the data scientists to be able to work at their tip-top ability and not have to need to devote more time towards learning the convoluted world of developer preferences, while also acknowledging that that very world exists for many good reasons and must be negotiated with. Metaflow came out of Netflix and is now supported by Outer Bounds. Metaflow understands and emphasizes the iterative nature of ML and AI projects and build to help both data scientists and developers integrate into each other's workflows seamlessly. They've spent a lot of time meeting developers where they already exist and giving data scientists tools to satisfy those developer workflows. ZenML has taken a different approach. They are a startup out of Germany that, in my experience, are meeting data scientists with Pythonic ways of making their work more accessible. Both of these platforms are wonderful, and if you get a chance to meet any of the team, definitely take it. Fila and Eddie from Outer Bounds and Hamza and Alexi from ZenML have all been so fantastic to get to know and wonderful to coordinate with on this. Alexi from ZenML even submitted some PRs to help make sure the code that I was showcasing would be tip-top for this particular video. So let's get into that then. What code will I be showing you? What is that code good for? And how do Metaflow and ZenML enhance the dev capabilities of the Spark and Strix Halo? So, let's get into some performance. Now, to be clear, these aren't strict scientific comparisons because, number one, it's not the point of this video. You can go to other creators like Jeff Geerling if you want true benchmarks. Number two, there are too many variables here. I've included the code on my GitHub if you want to run the tests yourself and control for various things if you want to run benchmarks. But we're more talking about experience and what these are good for. So first you'll notice that when I'm tunneling in, I'm exposing several ports. 10350 and 3000 are both for Metaflow, 8083 is for ZenML, although you can change all of those if you want. Those are just the defaults. Some disclosures here while we're getting started, so you can orient yourself really nicely. The Spark coding theme that I have is Grubbox, and the framework coding theme that I have is Capuchin. Next is that none of the functional code was written by an LLM. Any of the examples of this code were written by Metaflow as part of their sandbox demo, and I edited them by hand. The advanced NLP example is the only one where I can take full credit for it. I came up with the example and I wrote it all by hand. The LLM training example, the first one, is a heavily modified example written by TinyGraph for training GPT-2. However, all of the logging, all of the doc strings, and all of the comments were written by an LLM. So it will be very easy to tell. You'll see a lot of emojis and stuff going in the terminal. Both the Spark and the framework are using a VS Code tunnel. Although if I were to do this over again, I prefer Zed for opening a remote host. Because of how much Metaflow does in the way of automation, getting it up is a bit heavier and more complex, although they take care of pretty much all of the hard parts for you. You can keep track of progress in the terminal and in their UI that they open up. Once it's up, you need to run the shell command so that the Metaflow dev shell, so that the server in the background can be aware of the code running. The video here is going at 2 times speed, so it's not too long. Comparing the Spark and the framework running Metaflow, you'll notice, especially in the neural network portion, training MNIST on CPU, the framework is considerably faster. And if you look at the actual stats, it's because the Threadripper CPUs are beasts. They have 32 cores compared to the Spark's 20. On other CPU parallelized tasks, they're pretty similar as well. But once we get past the CPU tasks and into some GPU and NPU accelerated portions via TinyGrad, you'll see the Spark pull way ahead. This is not solely because of hardware or Metaflow, because Metaflow is just observing, making it easy to see what's happening, as well as making it nice to restart a particular job from a saved checkpoint if something goes wrong. So the reason you'll see the Spark pull ahead is because of CUDA. There isn't really a familiar API for accessing the Strix Halo NPU at this moment, and AMD doesn't even officially support it via RockN. If you look on the official, on the Rock, you will see it's unsupported. I truncated the result here, but at 1x speed, this whole training pipeline on the framework was still 14 minutes. So let's see the same pipelines written in ZenML. Because the examples were heavily drawn from Metaflow, I didn't change them too much except for the logging, and we had to change some stuff because Metaflow passes artifacts from function to function within a pipeline. ZenML has lower overhead than Metaflow, which is better in some ways, like it's a smaller resource footprint. So all of our code can run quicker, all the code that pushes to the very edge of the device's capabilities can run quicker. But it's worse in that it's a bit less reliable than Metaflow for business critical deployment workflows. Although you can make it more reliable, it's just not that way out of the box. I spent a good amount of time tuning up the GPU acceleration on the Spark for the ZenML pipeline, so you'll see on the framework that I'm just using cached steps, except for the NLP pipeline. This was just the first time I was running it. But I was doing that to try to get the TinyGrad LLM training quicker on the screen for a better comparison. So you see the CUDA accelerated TinyGrad versus what we tried to accelerate on the NPU. These videos are at 1x speed, so you can see the difference the smaller footprint and increased acceleration make. Here at the end, I add in the view of the ZenML UI for the Spark, and once it finishes, you can see the UI on the framework. All in all, both machines are excellent and are able to complete workloads in 5 minutes that literally take hours on my Dell Optiplex server, or triple that time on the Mac Studio, which is a crazy thing to say, because Mac Studio isn't hardware deficient by any means. It's just not made for parallel workloads using GPUs. I posit that the framework is best as either a gaming computer, which is why I recommend Bazite. It works flawlessly for everything except ML if you're running Bazite OS, or as the actual LLM server running Llama CPP in one of the QZO toolboxes, at least for now. If the hardware ever gets enough support that PyTorch could set the NPU as a device, then things could change pretty drastically. When you're going down this route, the main question I see people having is, what model should I pick? And while there's no guaranteed right answer, some models that I generally recommend on the framework are GLM 4.7 Flash, Nemotron Nano 30B, Qwen 3 Coder 30B, GPT OSS 120B. The next question usually comes after somebody gets their first overloaded context or out of memory error, and that is, how much context can I put in and how do I manage it? Well, the good news is that the QZO toolboxes have complete compatibility with the GGUF VRAM estimator script specifically for this, that this ships with every Llama C++ deployment. You just download any GGUF model and run this on it, and it'll estimate how many gigs of different amounts of context required, so you can make sure you're always running with enough memory to spare. More good news. Llama C++ has a router mode that allows you to select a folder full of models and then pick from them at runtime rather than having to pick only one model. The API for router mode also takes load and unload commands, so you can load a model you know you need at the beginning of a workflow to make sure it's completely ready by the time you actually need it later on. That brings up this point that loading and unloading models takes time. These are big, they are many gigabytes, so you have to plan for that. It's usually better to just pick one model and run the server with just one model. It's a little bit funny that I picked Qwen3 next to demo here. I think it's a pretty good balance of smart and also fast. It's just so verbose all the time, and you can see it in the reasoning. It generates like 1,000 tokens for no reason. So, my verdict, because of the lack of relevant support from AMD, this machine is a powerhouse that should probably only be used for LLM serving in the ML space, if it's going to be used for ML at all. The Threadripper is a beast that can be used for a lot, but you'd be putting it through too much. The DGX Spark is amazing in the right hands, but only in the right hands. Hands that love CUDA. If this is your first experience with CUDA, don't get a Spark. If you want a turnkey LLM server, don't get the Spark or the Strix Halo. Get the Mac Studio. That's the one I'm not talking about because it's not good for anything except that in this space. I've been using the Spark pretty extensively to take code I've already written that was already creating value, such as a comprehensive video processing pipeline that creates a data set from a video file using FFmpeg, Blip, Whisper Large v3, and Pianote, and productionizing it using the LLMs hosted on the framework. Many people wonder about using models small enough that they'd fit in 128 gigabytes of memory to vibe code, and I think that's actually the answer right there. I'm not vibe coding, I'm hiring an intern. The intern does things like look up syntax for me or do deep research into documentation that it just needs to parrot back to me. Writing a bash script or a function has never been the hard part of programming. Knowing which function to write and when to run it as part of a larger system is. That's what you pay engineers for. And that's what you don't trust LLMs to do. In this vein, as a huge Star Wars fan, I'm currently creating a full, and I mean full, set of definitive Star Wars datasets using the Spark, because 128 gigabytes of CUDA is more than even like an RTX 6000 Pro, which only has 96. I don't need it to go that fast, I just need it to get done reliably. I thought about showing you a comparison here of the same Star Wars dataset pipeline running on both CPU and GPU, but while I was trying to strategize for that, I figured it wasn't too difficult to conceptualize that processing a 2.5 hour movie took 6.5 hours on CPU, but only 1 hour on GPU. I don't think I can overemphasize how out of reach this project is normally. Nobody just randomly has 25 terabytes of storage sitting around, nor do people normally have over 100 gigabytes of CUDA accelerated VRAM ready to go for parallelizing frame extraction with frame description, speaker diarization, and transcription all at once. It's not out of reach because of hardware, it's out of reach because who has weeks to just let their gaming PC or dev machine try to sort all that out? That's where a dedicated ML server like the Spark comes in and shines. Earlier, when I ran TinyGrad training GPT-2, I'm sure some of you looked at that and went, this is so dumb. GPT-2 hasn't been state-of-the-art since 2018. You're right. And that's the main place that the Spark really shines beyond any other consumer machine on the market right now. The lowest priced 5090s on Newegg, eBay, and Amazon right now all cost more than the Founders Edition Spark, and way more than like the Asus Ascent GX10, which is the same as the Spark, just not in a gold box, and it's only $3K. And you can 100% train Gemma 3.4b on the 5090, and you can likely do it without streaming your dataset, which is sick. But you know what you can't do? Fine-tune Qwen 330B or GPT-OSS 120B or GLM 4.7 Flash. I showcase the basics of making this work for any dataset too. Conversational, instruct, GRPO. You just need to get it into text datasets and you're golden. I found in my testing that if I estimate 40 to 60 seconds per training example, I get a pretty good estimate of how long the training will go, because that's how fast it is. Huge shout out to my friends at Unsloth, VLM, and Hugging Face. You guys are heroes in my book. I've seen some people talk about the Spark powering off under heavy load, and I kind of hate to be that guy, but I haven't experienced that at all, and neither have the others I know who have bought the Spark. I don't mean to discredit anyone here, but my experience just hasn't matched with that. Hopefully it makes sense then why I'd recommend picking up both of these, or at least following the pattern of one ML dev server and one ML inference server as you're building an ML home lab. Train good models on one, the ML dev server, run the model on the ML inference server, and then develop agentic systems using the trained models on the first. Any AI engineer will tell you how difficult agentic RAG is to nail down. Drilling down into context engineering, you hit philosophy and deep linguistics so fast, because the crux of the matter is, to do good RAG, you need to have access to the correct answer before the question is asked. Find that answer at runtime and give it to the model to narrow the distribution for generation. Cloud compute is really tempting here until you start looking at actual prices. For example, did you know that you can buy 3 H100 GPUs on eBay for the cost of renting 8 for 1 month at Google or Amazon or Azure? Beyond that, Exo just released a blog and update showing one of my favorite things, combining hardware that wasn't meant to go together and allowing each piece to shine doing what it's best at. For a high-throughput LLM endpoint, you can allow the Spark to pre-fill tokens using the Spark's GPU and VRAM, then allow the Mac Studio to decode with metal acceleration. For those of you that stuck around, it should make sense why I had a Spark setting in Mac Studio ablaze at the beginning. Sparks and Macs go together now. If you've made it this far, thank you sincerely for sticking it out with me. This video took 4 months to produce, and I hope you're getting value out of it. In an effort to provide more value, I'm currently implementing open source and free-to-run versions of many of the deep learning AI courses, along with some others from Coursera, and in part thanks to my friends at AI Makerspace on Maven. Hey Dr. Greg, hey Chris. You shouldn't have to pay to run educational code that teaches you how to be a better AI engineer, especially during a time where everyone is learning and everyone feels behind. Whether you're a researcher or whether you're Andre Karpathy, everyone feels behind. That doesn't mean that you are. On that note, I'd like to thank you just one more time. Thanks for being in this together. Thanks for experimenting together. Build, ship, share.